Hello everyone. In the last video we started talking about integration to determine volumes, and we introduced that by using integration to find a volume of a cylinder. And that was of course something that could have been done with geometric formulas, but we proved that we could find it with an integration method, and that integration method was the disk method. The disk method involves using multiple disks to determine the volume of a solid of revolution. So a solid of revolution is when we take a function and we find its area under a curve and then we rotate that around an axis. So if I have a function like this, say, this drawing is probably not going to be very good, and I do apologize for that. So here's our surface, or sorry, here's our solid here. And the way that we do this is we take little disks. So say this is a disk. This is a disk right here, and we use this disk to determine the value of this volume here in this little disk area. And then the height of this little disk, or the width here, is going to be delta x. And we have these disks running all the way across our solid. And of course, as these disks get narrower, so as we have those delta x's approach dx's, then we're going to get a perfect volume for this region. So now that we've got that review covered, why don't we do an example? So this is going to be one that we couldn't do with an algebraic formula. So this is where it gets pretty important that we know how to deal with this. So we're going to be finding the volume obtained by rotating the square root of x around the x-axis between 0 and 6. All right. Again, super important that we draw this out. So here's our graph. And so here's 0, and let's say this is 6. We know what our value, we know what our square root function looks like. It's something like that. There we go. And we are going to be, this is our end point here. So we're really finding the area in there and in there. So we're finding this volume in here. So what we need to do first is we need to set up our problem. So note that the volume is going to be equal to the integral between 0 and 6 of our a of x dx. Now our a of x function is the disk, so that's the that area of the disk. So we can obtain that by taking a of x equal to pi r squared. Now our radius is just the function. Our distance away from the x-axis is the value of the function. So we take pi times f of x squared, and that gives us pi times the square root of x squared, and that gives us pi times x. Now that's going to be pretty easy, because now what we need to do is now we need to plug that pi x back into our a of x function. So now we're going to get the volume is equal to the integral between 0 and 6 of pi x dx. We can pull out that pi since that's not reliant on x, and then this is a simple monomial integral where the x is lifted by a power of 2 and then divided again by 2. So that gives us pi times 1/2 times x squared evaluated between 0 and 6. And if we square 6, that gives us 36. That 0 term cancels out. That gives us pi times 1/2 times 36. Of course, 1/2 of 36 is 18. That gives us 18 times pi. So that is the volume inside of this whole big region that we have in here. All right, let's do a proof here. So this is going to be kind of similar to what we did in the first video, but we're going to be proving the volume of a sphere. We're going to prove that formula. We know what that formula is from our days of geometry back in early high school. So what we need to do here is we need to prove the formula for the volume of a sphere of radius r. And that formula is 4/3 times pi r cubed. All right, so let's draw this out. So we're going to have a sphere here. This looks more like an egg, but that's a sphere. Let's call that a sphere. Here's our equator. our equatorial line there. And what we are going to do is we are going to integrate along x. So here we have our point negative r, and here we have our point r. So we're going to integrate along x. Now, what is our function value going to be? So our height here. So we have that our y, so our height y, well, we know that y is equal, with the Pythagorean theorem, y is equal to r squared minus x squared, because here we have our r's, or sorry, here we have our r, and here we have our x, and here we have our y. So there we go, there's our y. And disregard this other red line though. So now what we can do is we can determine our a of x value. So if we know that y is equal to r squared, the square root of r squared minus x squared, then our a of x is going to be equal to pi y squared, which means that we're going to get a of x equal to pi times r squared minus x squared. Now we are prepared to pull this into the integral. We know our endpoints are negative r and r since we're integrating along the x-axis. So we get the volume is equal to the integral between negative r and r of a of x dx, which is equal to the integral from negative r to r of pi times r squared minus x squared dx. Now what we can do is we can use that integral identity where we can, if it's an even function, since this is a sphere, we can use it as an even function. Then what we do is we pull out the pi, and we multiply the integral by 2 and arrange our integral bounds to suit our new identity that we've used. So that gives us the volume equal to 2 pi times the integral from 0 to r of r squared minus x squared dx. That ends up to be 2 pi times, now r squared is not dependent on x, so we just tack on an x because we're treating r squared as a constant. That gives us 2 pi times r squared x minus 1/3 x cubed, evaluated between 0 and r. Again, we can disregard that 0 because that will cancel out, and we can just use r here. So we get the volume is equal to 2 pi times r cubed minus 1/3 r cubed, and that is equal to 4/3 pi r cubed, which is the formula that we had at the beginning of the problem. Well, thank you very much for watching this video of 3 deviations. In the next video, we're going to be looking at rotating these regions, kind of using those area between curve ideas that we were doing a couple videos ago, but in this next time we're going to be looking at when we need to rotate that about an axis. All right, so we look forward to that, and we'll see you guys in the next one.